Thank you, Jaeheung. It's always a pleasure to come to Korea. Hi everyone, my name is William, and I'm one of Usama's PhD students working in the Stanford Robotics Lab. And it's my honor to be presenting our work titled Robust Implementation of the Artificial Potential Field. To start this presentation, I have to go back 40 years. So this is, okay, I have some music, but maybe. So 4 years ago, Usama formulated the artificial potential field. So the manipulator is programmed to travel in a straight line, and that's Usama 40 years ago. And so when the Sumi house is placed on the table, the manipulator avoids the obstacle in real time using the artificial potential field. And sorry, am I going too fast? Maybe a little bit slower. Oh, it's okay. Okay. Okay, cool. And now, so here's the crazy kitchen. So because you have stuff flying at you. So basically, it's what I'm showing is the under-actuated multitask cumulative control with simultaneous smooth multi-collision avoidance and joint limit avoidance using the artificial potential field. So I want to motivate the work with this crazy kitchen. Okay, cool. So first, to lay the foundations, I'm sure you guys are all aware. So our proposed methodology is formulated within the constraint consistent whole body control framework. So take, for example, the task of cleaning the glass window here while maintaining multiple tasks such as posture. For example, readjusting your posture to move to a goal position, task behavior such as your head, multiple contexts, various constraints such as obstacles and balance. So the framework enables strict hierarchical dynamically decoupled multitask control, where controllers for each task listed are executed in parallel. And the control input to the robot is the total control torques from all tasks, where task hierarchy is enforced using task consistency and dynamically consistent null space projectors. So altogether, the framework provides a very powerful methodology for controlling high degrees of freedom robots. So this is the foundation for this existing work that I'm presenting. And so with this type of framework, you can achieve cool stuff like multi-contact control. So this is, for example, balancing on slippery moving surfaces using the framework and while respecting friction cone constraints, for example. Oh, yeah, I think that's pretty smooth on my side. Okay, so yeah, I don't know if I could fix that. I think it's possible. Yeah, I'll try it out. Okay, so let me first talk about the artificial potential field. I'm sure you guys are all aware of it. So the seminal paper introducing the APF was published in 1986 by Osama. So just for a brief primer, the APF is described by the indicated potential function as shown. This is characterized by a zone influence parameter rho, 0, and a gain parameter eta, where rho is the robust distance to obstacle. And so using the artificial potential field, attractive potentials to goals and repulsive potentials from obstacles can be created, where the gradient of the potential field is applied as a force to a robot. And this is also known as the Frost function. So I'll be using a series of 2D scenarios shown in the bottom left to motivate our approach and our robust implementation of the APF. So in the bottom left, you can see this animation. The blue puck is the robot. The pink object represents the obstacle, which is modeled as an ellipsoid, and the green puck represents the goal. So the pink zone around the obstacle represents the zone influence of the artificial potential field associated with the obstacle. And finally, the green line indicates the closest densest vector from the robot to the obstacle. So I'll be using this simple 2D planar example to motivate the work. Okay, so first of all, high momentum entry into the constraint zone influence may cause oscillations and APF force ramping from conflicts between task and the repulsive potential. And this is through task-induced high momentum entry, as shown in the video. Oh, okay, yeah. You guys can't see it. It's okay. Yeah, okay. So this in conventional APF implementations, this necessitates careful parameter tuning to mitigate this behavior for a variety of scenarios, which includes highly nonlinear, high degree of freedom systems under constraints. So let me talk about the approach to address the previous issues. So first, using the constraint consistent whole body control framework as a foundation, the artificial potential field is incorporated into constraint task in task hierarchy, as shown in the bottom left. So we propose to augment this method by introducing an outer velocity control zone around obstacles to reduce entry momentum into the potential field zone of influence, and a strategy to smoothly depart obstacle zones and thus the constraint task within the whole body control framework. So I will go back to the 2D planar example to talk about how each of these plays a role in the robust implementation of the APF. So within the whole body control framework, the APF is incorporated into constraint tasks as placed at a higher task priority than the control task. By doing this, the control task component in the constraint direction will be removed. So this is observed in the first video where the robot's trajectory follows a contour of the zone influence until it exits the zone. So this removes the control task conflict with a constraint task. However, as you can see in the second video, when the robot has higher momentum, then there's still a large deflection observed due to the potential field of force ramping, which is not good. So there are two remaining issues. First is how to prevent task-induced high momentum entry, which is addressed by the outer velocity controlled zone. And second is how to smoothly exit the APF constraint task. This is addressed by an exit strategy conditioned on the control task moving the robot away from the obstacle. The second issue is highlighted in the first video, where the control task is modified until the robot leaves the zone influence. Instead, to smoothly depart from obstacles, the unmodified control task should be allowed to move the robot away, as that is what the robot task behavior is. So additionally, if the robot stays inside the zone influence, then there are issues, for example, when the goal changes in the constraint direction as the control task forces are removed in that direction. Okay, so to address the first problem, an outer velocity controlled zone is added outside of the APF zone influence. So I call this row 1 instead of row 0. So in this zone, if the obstacle directly affects the control link, then we can apply a maximum velocity saturation control where the maximum velocity is smoothly reduced to a nominal lower velocity as the robot approaches the inner zone influence, as shown in the graph to the right. This is achieved using the goal position velocity saturation controller, as shown in the bottom right. Otherwise, velocity damping is used, for example, in joint limits. The outer zone can be determined beforehand or dynamically based on the robot's approach velocity towards the obstacle. So if the velocity is extremely high, then the row 1 can be dynamically determined from that to be larger. So the video demonstrates the added effect of the velocity control zone, where minimal deflection is observed at entry into the inner zone influence, and the robot returns to regular operating velocities when exiting the outer zone following the same maximum velocity saturation curve. However, as you can see, there's a non-smooth exit when the robot leaves the zone of influence. There. Yeah, so then we need this exit strategy for resolving this. Okay, so again, the exit strategy is needed with the framework to depart obstacles smoothly. This is generally in the framework of how do you do task transitions within the strict task hierarchy. The exit strategy for the constraint task is predicated on checking if the control task wants to move the robot away from the obstacles. So using the same 2D example, the video shows that the robot executes the control task when the control force is in the half plane facing away from the current closest distance vector. This results in the straight line trajectory leaving the zone influence, which is the unmodified control task behavior. So for a general robot, we achieve this by projecting the control torques onto each constraint direction using the dynamically consistent inverse Jacobian. So that's on the right, J bar. To get the controlled force applied in that direction and exit constraint task if the dot product is less than 0 and the projected force is above the threshold. So this force threshold is quite important to choose. It can be set to a fixed value, but more importantly, it should be taken as the potential field force at the current distance. So these conditions can be also checked over a time window for robustness. So as a reminder, although I used 2D examples for demonstrating our approach, the approach is extended to general robots using the constraint consistent whole body control framework. Now the question for the entering scenario is mitigated by the outer velocity control zone. So yeah. So it's my general opinion that it's okay for this type of control torque jump as long as your behavior is this. Yeah. Okay. So for multiple obstacles, yeah. So the multiple obstacles are naturally handled by the whole body control hierarchy. So this is an example of multiple obstacles, and it navigates in between the two obstacles quite well. So this addresses the multiple obstacles issue naturally. Okay, so for experimental validation, I did 3 experiments. So first is virtual joint limits, second is self-collision avoidance, and lastly is multi-collision avoidance. So for the first experiment, the elbow joint of the panda is given virtual limits as shown by the red indicator, sector indicator. As seen in the first video, the command of motion is a straight line trajectory up and down, starting from an initial pose while holding its initial orientation. In the second video, the baseline implementation results in oscillations due to the high entry joint momentum with the APF field parameters. Yeah. And in the third video, the approach is shown where the joint experiences no oscillations approaching the virtual joint limit and smoothly exits the joint constraint zone influence using the control task. And yeah, I think the video is choppy. Yeah, it's not work, I think. I have a plot. You can imagine the joint trajectory with the plot. So here are the trajectory plots comparing the baseline and approach. So the black dotted lines represent the virtual limit, and the red dotted line indicates the zone influence boundary, which is around 8 degrees, and the orange dotted line represents the outer velocity zone boundary, which is 12 degrees. So the right plot demonstrates smooth joint motion when approaching, entering and leaving the joint zone influence using our proposed approach. And most importantly to note, the joint has some stiction, so this causes the joint to remain inside the zone influence. So without the exit strategy, the constraint task will always be active, and you can never exit this constraint task otherwise. Okay, so in this next experiment, self-collision avoidance is performed, where the robot attempts to move in a straight line trajectory, which will cause collision with its lower links. So the lines indicate the closest distance vector, where red lines indicate active constraints. And I used the signed volume GJK method to compute these vectors at 1 kilohertz using the robot's convex collision meshes. So in the baseline approach on the left, oscillations are observed when traversing around the lower links. And in the second video, the same experiment is performed using the approach where the end effector reduces its velocity approaching self-collision and smoothly traverses around its lower links. And eventually the robot exits the constraint task and restores its normal operational velocity. And to note, this is a very fast approach velocity. It's about 6 centimeters per second here. So yeah, it's unfortunate that you can't see the video, but it's quite dramatic bouncing. And here's the trajectory plots comparing the baseline and proposed method. And it shows the smoothness of the proposed method. And the lower links are rendered with respect to the end effector to highlight the relevant links approaching self-collision. Yeah. And here is the It's like collision avoidance with a bottle, so I'll just play it. Okay, the video's pretty bad. It's very smooth, trust me. Yeah, so this is an SRC sensor in the kitchen. Okay, cool. So that's my final slide, and in conclusion, represents a robust implementation of the APF. So first, we introduced an outer velocity control zone for reducing high momentum entry. Second, we designed an exit strategy for departing obstacles. And finally, we integrate everything within the constraint consistent whole body control framework. Thank you, and open for questions.